I'm going to take the next 5 minutes to take technical questions about it. And I'm saying technical because following, I have about 15 minutes of various thought leaders, entrepreneurs in this space, answering some of the market questions. Is there anybody that has any questions around how Superhot works? Okay.
Yes, thank you. My question has to do with what are the key technical barriers or challenges that you need to overcome and test in the field, that you need to take from the lab to the field?
If you can think back to that process flow diagram, I think it's best positioned in that way. So the question is, what are the key technical barriers? The most important one, the proof of life, is in the reservoir, is in our ability to absorb adequate heat at 400 degrees. It's understanding the rock and those fractures. This zone at 400 degrees Celsius and 220 pascals is known as the brittle ductile zone. In the words you can imagine, it is both brittle and ductile. We don't know how it will respond over time. We need continuous flow, at least 6 months of demonstration. That is a key approach. It's not expected necessarily to be a technology. The next is, of course, that drilling, getting to anywhere. We see millimeter wave drilling, we see plasma drilling, and we see diamond bit increase in speed. But getting to anywhere via drilling technology is a key hurdle. And I would say a very distant third is optimizing that above ground equipment that we talked about in the steam generation. Any other questions?
Thank you. So my question is, you mentioned the brittle ductile zone. So are there concerns with messing with seismic activity when digging that deep? Thank you.
Thanks. Great question. Has to happen. What we know is that geothermal activity has been linked to nuisance seismicity. However, what we don't know is how that brittle ductile zone will respond. Now, there are many ways in which the conventional geothermal community has reduced and mitigated that risk to a point in which all countries are quite comfortable with it. I expect the same type of regulatory and site selection process to help mitigate that risk of known fault zones. But again, this comes back to the need to understand the rock mechanics. For example, we need a laboratory where you can take a meter by meter sample and test it. And I think we're close to getting one of those online. Any other questions? All right, with that, I can take it from here, Brianna. Oh, yeah, I will. Thank you. That's a great point. All right, I am going to introduce, as you guys can imagine, this is a pretty nascent industry in which our leaders are not necessarily prioritizing a 30-hour flight to Egypt, but they will in the future. So first, I'm going to start in the top left-hand corner, Carlos Araque. Carlos is the CEO of Quaise. They are a super hot rock energy development company focusing primarily on the drilling technology. It is Carlos's company, and you guys are welcome to come up afterward to check this out, that is using a millimeter wave to effectively, so that is a laser, to effectively evaporate the rock. This is a sample from his lab. Next, we'll see Tony Pink. Tony Pink is the Vice President of Subsurface Energy and is also currently their lead geothermal. NOV, for those that don't know, are a world leader in oil and gas services and a very strong technology company. You guys going to have to hang with me here. Guðmundur Ómar Friðleifsson. He is the chief scientist in Iceland at the IDDP projects. His observations are unique to everybody here. He is the only one that has operated facilities and wells at the supercritical conditions. Now, in Iceland, that happens to be naturally occurring hydrothermal reservoirs, but his observations are very important. Hiroshi Asanuma, Dr. Asanuma. He is the Deputy Director of the Geothermal Team at AIST, which is a renewable energy, very specifically a geothermal research institute in Japan. Japan is very forward-thinking on how they're going to manage this supercritical resource, and it's a large part of their solution. Bailey Schwarz is the lead engineer for Eavor Technologies. Eavor is a startup in the geothermal and the superhot rock space. They do what is called a closed-loop service. So when you think about that process, they don't move through fractures, they move through drilled conduit. Finally, Araque Ingersoll. He's the co-founder and managing director of LucidCatalyst, TerraPraxis, and a co-founder of Synergetic Solutions. He offers a lot of thought leadership on how this solution, this energy solution, can drive our future economy, specifically around hydrogen. The first question that a handful of these thought leaders are going to respond to is a question around what is the potential. Here you'll find Araque expanding a little bit more upon the opportunities within green hydrogen, and you'll also hear a bit more from Dr. Friðleifsson giving his insights on what he's actually observing in the field.
Superhot rock is very unusual and quite different from conventional geothermal because superhot rock resources are extensive, meaning they are spread out over large areas. And this will enable many projects to be developed in these heat basins or in these geologic areas where there are heat resources available. And because the surface works, the stuff that has to be on the surface and visible is really quite small and has a very small footprint, we see that it will be possible to build many, many projects in these regions. Also, the resources for high temperature geothermal are quite large. So if you have an area where you can build a high temperature geothermal project, it's likely that you can build many projects and have potentially hundreds or thousands of megawatts of high temperature geothermal production.
YTDP-1 was the world's hottest production well, producing 452-degree hot superheated steam at 142 bar melted pressure. The maximum power output was about 36 megawatt, which is about 7 times the world average for a typical geothermal well. You must realize that the energy stored in the earth crust alone, on our scale, is, so to speak, limitless. And the key question is, how fast can we develop this new approach to make any difference to the climate changes that we are dealing with at the moment?
We have estimates that 100 megawatt of electricity can be generated for more than 30 or 40 years from each supercritical geothermal system. Because of the potential of the supercritical will reach 10 gigawatts or more, which can replace all the coal power generation systems. So that's why we are very motivated to develop supercritical.
Superhot rock geothermal has an amazing potential to increase the efficiency and lower the cost of hydrogen production. This is because it enables the most efficient electrolysis because of the high temperature heat that's available, and because it has low energy cost, low electricity cost, and a very high capacity factor. It enables a very efficient use of the electrolysis capital equipment. It also can create a market for exporting hydrogen and derivative products like ammonia from countries that will have large geothermal resources, more than they can use internally.
So my vision for superhot rock energy is that it can deliver on the true promise of geothermal. I think with the right technological developments and breakthroughs coming online in the next 10 years, geothermal and superhot rock geothermal in particular can become the workhorse of the energy transition, can provide as much as 50% of primary energy supply for the world by 2050. So we're talking about 90% plus of humanity having access to geothermal right where they are.
All right. As you can see, the promise is limitless and huge. However, I hope that you enjoy their candor here as well, because when I asked them of the challenges, they did not shy away. Now, granted, they are also working hard to overcome these challenges, but again, the candor is refreshing.
So for super hot rock geothermal to come true, we have to work on a few groundbreaking technologies. I like to think of two main gatekeeping technologies for this to scale. The first one is drilling deeper, hotter, and faster. You know, there's no question that in order to unlock geothermal at the multi-terawatt scale, we have to access hot rock, super hot rock, at greater depths and at greater temperatures. That's what's currently possible with drilling technologies in oil and gas. The second one is to extract the heat. So creating permeability in the basement rock is going to be an important component of this too. That usually means creating permeability or enhancing permeability from what's naturally there to be able to circulate a fluid through the rock and be able to extract heat rates with the potential to repower most of our fossil fire power generation in the world. To make it a true global contributor, we need more investment into drilling and investment into extraction, the two key technologies that I think are going to be necessary to scale.
Yeah, what we hope to demonstrate, I mean, one of the main obstacle or problem, if you like, with harvesting superhot fluids at high pressures are the extreme forces that superhot fluid exerts on the material used in superhot wells. Like the several kilometers of steel casings from surface down to great depths, the cement to fasten to the rock wall, the wellhead walls on the surface, etc., etc. So there are some obstacles here. But the conventional materials for drill hole casings, for instance, are simply not of high enough quality to sustain the enormous stresses we need to deal with in supercritical or superhot.
Yeah, so the big problems that need to be solved are being able to break a lot of hard rock quickly, dropping the temperature of the fluid so we can drill these wells in a normal way, and cooling the formation enough to run a non-exotic completion into the well. Those three things, and then rapid iteration of those three things will get us there. And then we need a commercial framework that's going to help us achieve those goals. Yeah. We have to get governments and local authorities, get them out of the way. The permitting process has to be solid, but expedient. Yeah. Slow and solid, and it's a 3-year permitting process is not helping any of us, because if we go from one iteration, 3-year gap, one iteration, we're going to set this back by 5 years to a decade. Yeah.
I just want to double click on two things that came up there. Earlier, I was asked what the technology hurdles are. I think Dr. Friðleifsson did a nice job of capturing one I overlooked, which is metallurgy. At these higher temperatures and higher pressures, we expect the metal to give sooner. We need more research in metallurgy and the cements that go behind them. Finally, what Tony said here, I would not consider this a technical hurdle, but it's an important one. Permitting can be overwhelming and very slow because this is so nascent and everybody is learning it again for the first time. We need more investment in our regulatory structures so that we can move people into the field quicker and iterate faster. Needless to say, I then asked them, after asking what the hurdles are, what they're doing about it.
So for super hot rock geothermal to come true, we have to work on a few groundbreaking technologies. I like to think of two main. So Quaise's role in superhot rock energy has very much to do with drilling deeper, hotter, and faster. We have a new drilling system which uses conventional drilling from oil and gas to get to the basement rock. And once we're in the basement, we use millimeter wave drilling, which is an energy-based method to vaporize rock to rock. We think we can get to deeper rock with a linear increase in cost as opposed to exponential. And we think we can truly open up this new frontier in geothermal by providing global access to these resources.
So the New Mexico project is proving out some of our core innovations to allow us to access super hot rock. Most importantly, our proprietary cooling technologies. So basically what this lets us do is drill really high temperature rock efficiently by tackling the problem by actually cooling our bottom hole assemblies. So we're able to use conventional off-the-shelf technologies rather than kind of going the opposite direction, trying to redesign all of the elements, the electronics and sensors downhole to withstand really, really high temperatures. So it's kind of approaching the problem a different way to allow us to use, all of the conventional off-the-shelf proven technologies to access super hot rock. By unlocking this ability to scale geothermal, we're essentially building out a solution that can allow super hot rock to be basically installed anywhere in the world.
And we've seen from other programmatic drilling activities, such as oil and gas drilling and large-scale geothermal development in the Philippines and Indonesia, that the cost per well goes way down when you're repeatedly drilling in the same kind of geology. And the fundamental cost of super hot rock is the wells. So if you can have a kind of industrial process to learn and repeat wells over and over again in a similar geological set of conditions, this is the optimal situation to drive down the cost of drilling. If you drive down the cost of drilling and have a standardized power plant that you're building on the surface, you can achieve extraordinarily low costs of energy.
By ITDP3, which will be drilled in the coming year, I expect higher quality materials and newly developed technique to deal with the extreme forces will be used. High quality casings are already available on the market, for instance, the Timmetal 475 from Timmet, and the so-called flexible couplings developed by our team during our ITDP effort so far are also already marketed.
When I first moved to the United States, drilling shale, the wells in the Permian Basin took 80 days. That same well takes 15 days now. Or we have to just do the same in geothermal, and that is drilling lots of holes and getting better and better at doing things. We have the ability to get down to super hot, dry rock with just some big jumps in technology, but not jumps in technology that require a scientific revolution or something. It's all doable from an extension of what we're currently doing. Yeah, it's not easy, but it's all doable. Nothing should be scaring anyone who already drills down to those depths of just doing it in a hotter and tougher environment.
A lot of common themes here. Coming back to the energy trifecta and that three-legged stool. You can imagine the venture capitalists in the room here. How big's your market? How cheap are you going to make it? That's what they focus on, because that's the only way it's going to hit mass deployment. So we're going to wrap this up with one last very quick question where I ask them to effectively paint a picture of what is the future.
Last year, Japanese government modified the strategy for the reduction of the carbon dioxide by 2050. Three technologies are included in the power generation. One is photovoltaic, high efficient photovoltaic, and the other one is the offshore wind turbine, and the third is the supercritical geothermal. So the government people are very expecting for the development of the supercritical. So that's why the government is full funding to the supercritical geothermal project in Japan now.
But by proving the method in one superhot geothermal system like in Krafla, in northeast Iceland, That should open the path to worldwide application of creating magma-driven ETS geothermal systems.
I believe by 2024, 25, we will have proven the concept of super hot rock drilling. Once that proof statement hits the road, then it's a scaling investment, commercialization, rapid ramp up.
We know that the market is ready. There's a lot of interest from companies with 24/7 carbon-free emissions targets, grid operators that really like the distributed characteristics of our solution and are looking for grid stability solutions. Basically widespread interest from across the board for both the electricity and the heat market. So as soon as we've reached this next hurdle of having some commercial projects in the ground, we expect that there's going to be a rapid uptake of this technology.
As we develop the capabilities of the technology, the ability to reach the heat that's required through deeper wells and deeper projects will spread this capability out much more broadly around the world. And ultimately, a large number of the countries, possibly most of the countries in the world, will be able to develop their deep heat resources and become energy independent.
The timeline to expand superhot rock can already start now, right? I think that's an important point. I think we can bring some of these resources online in the next 3 to 5 years if we start developing them intentionally right now with existing technologies. But to bring them to all of humanity, we're talking about the better part of the next 10 years or so. So to me, developing breakthrough technology always takes time, always takes effort. 10 years is the typical timeline I give to breakthrough innovations. And those 10 years begin that pathway, right? So Quaise, for example, is trying to repower the first power plant by the end of the decade. But once you prove that, then you have a pathway to repeating that process many, many times over with the existing fossil-fired infrastructure and human capital base in the world, right? So the race is on to 2050, right? Getting to net zero by 2050 is going to be the timeline over which super hot rock plays out. But we can already bring some resources online now in the next 3 to 5 years, and more importantly, open the pathway for super hot rock everywhere within the next 10 years or so. We should invest now in places where we can already do this, get better, improve the economics, and with a technology-driven background, eventually take it everywhere in the world.
I want to wrap up here. It's hard to beat Carlos. He speaks so eloquently. But I want to emphasize one thing. We are woefully underfunded. When you think about the potential impact of superhot rock and where we are in the maturity cycle, woefully underfunded. And we need to do it now. I also wanted to emphasize something that came from Dr. Asanuma. He described the Japan's plan to get net zero by 2050. And in doing so, he took geothermal out of the other bucket. I encourage you, whenever you can, to consider geothermal not in the bucket of everything that is left over, but actually look at it at the potential and the size that it actually can have. Finally, I want to talk about the scale, specifically using options to get to scale. You see, my girls, they're going to be here, perhaps not at COP, on this earth in 2100. Yet we continue to set our goals 10 years at a time with small paths and looking at optimizing solar or finding a more efficient way of getting wind out there. We need more options and we need to invest today because the scale of the problem becomes exponential in 2100. And I think superhot rock can get there with investment, patient, large-scale investment internationally today. Thank you, guys.